In this video, we're going to talk about vapor pressure lowering. Vapor pressure lowering is a colligative property. Now, it's been a while, so we'll go back. A colligative property is something that depends on the concentration of the solute, but not the identity of the solute. And there are four that we're going to be looking at. This has three: boiling point elevation, freezing point depression, osmotic pressure, and the fourth one is vapor pressure lowering. So these are the four colligative properties that we're going to be paying attention to. And we did the concentration units because of the fact that you need, for the boiling point depression, you're going to need molality. For the for the freezing point depression and boiling point elevation, you need molality. For osmotic pressure, you need the molarity. And for the vapor pressure lowering, we're going to need mole fractions. Okay, so this figure here shows pure water. Okay, and so I have water molecules in a liquid form and a gaseous form. So we're talking about how many molecules are in the gaseous form. And so if I count these, you'll see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 water molecules in the gas. Okay, and then I add these. For this one on the right, it is the aqueous solution, which means a water-based solution, and I've added these other molecules. So these blue molecules, and the identity of the blue molecules doesn't matter. We can say it's sugar, okay? So it doesn't really matter. But by adding some molecule to this water, okay, then what happens is that I count, and I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 water molecules in a gas, in the gas phase. Okay, so by adding something to my water, I reduced the vapor pressure, or the number of molecules of vapor that are present. Okay, and this formula basically says that the vapor pressure lowering, which we're going to symbolize that by delta P, okay, so delta P is equal to the pressure of the pure solvent minus the vapor pressure of the solution. So that's basically what the vapor pressure definition is. So Riyalt was the one that proposed this relationship between dissolving something and the vapor pressure. And so Riyalt's law is this definition: the partial pressure of the solvent over a solution equals the vapor pressure of the pure solvent times the mole fraction of the solution. Mole fraction of the solvent. And so that's basically, this definition is this formula. The pressure of the solution is the vapor pressure of the solvent times the mole fraction of solvent. So there's a couple different things that you need to remember from here. Is that A is solvent versus B, and B is down here at the bottom of the slide. B is the solute. Okay, and by saying P naught, this naught here means pure, in this case pure solvent, but in pure solvent. Okay, so this would be the vapor pressure of the pure solvent by adding this naught. So this one is the solution because it doesn't have the naught, and this is the solvent. Okay, and so Riyalt's law only holds true for dilute solutions. So this is a plot of what Riyalt predicted, is that there's a linear relationship between the vapor pressure and the mole fraction of the solvent. However, when experiments were done, it was found that only at very dilute solutions, or when I had mole fractions of the solvent that were really high, above 0.9, that the ideal, or the real life, equaled that of the predictions. Okay, so we're going to be focusing on these solutions that have a mole fraction of the solvent greater than 0.9. It could be even a little bit less than that, but 0.9 is a good number to pick. Okay, And so we can also say that the vapor pressure, the change in vapor pressure, again, that's the solvent minus the solution, is the vapor pressure of the pure solvent times the mole fraction of the solute. So we have three different equations that we can use now, and the other equation that was from the other page was simply that the change in pressure is that of the pure pressure of A minus the pressure, not there, there's a not there, of A. So this is the pure solvent and this is of the solution. So we have three different equations that we can use with this. Okay? So the first problem is the solution is prepared by dissolving 396 grams of sucrose. So grams is mass. So I have a mass, and it's 396 grams of C12H22O11, and 624 grams of water. So it's another mass. I have a mass of 624 grams of water. It wants to know what's the vapor pressure of the solution, so it wants to know what P is of water, because that's my solvent. I have a temperature of 30 degrees C. It tells me the vapor pressure of water, so P naught of water, is 31.8 millimeters of mercury, again at 30 degrees, and then it gives me the molar mass of my C12H22O11. Okay, so it wants the new vapor pressure. So of the three equations, the easiest one to use is that the pressure of water is going to be the pressure of the pure water times the mole fraction of water, and that gets me straight to where I want to go. Okay, so while I have the vapor pressure of water, the vapor pressure of pure water, I do not have the mole fraction of water. Okay, and if we go back, mole fraction of water is going to be my moles, we go by symbols, N of water over N of water plus N of the C12H22O11. So I have to find the moles of water and the moles of the sucrose. Okay, so N of water. So I gave you the molar mass, I didn't write it down. The molar mass of the C12H22 is 342.34 grams per mole. Turns out we need the molar mass of water, and that's 18.02 grams per mole. Okay, so the moles of water is the mass of water divided by the molar mass of water. So it's going to be the 624 grams divided by 18.02, and so I get, when I do that, 34.63 moles of water. Okay, I need to find the moles of the C12H22O11. Okay, and I'm going to do the same thing. It's going to be the mass, oh that was real bad, of C12H22O11 divided by the molar mass of C12H22O11. So that's going to be the 396 grams divided by the 342.34 grams per mole. So the moles of that is 1.157 of C12H22O11. So therefore, now going back to this equation, so bringing this equation down, the mole fraction of water is going to be the 34.63 divided by the sum of 34.63 plus the 1.157, and I got 0.9676, and there's no units for that. Okay. Alright, and so now that I have the mole fraction, change colors here, now I have both the pressure of the pure vapor pressure of the pure water, and I have the mole fraction of water. Now I'm going to use this equation and that my pressure of water is going to be this pressure of water, which is 31.8, and I write it 2, 31.8 times the 0.9676. And because of the fact that this doesn't have a unit, this is in millimeters of mercury, my answer is going to be in millimeters of mercury. And I get 30.8 millimeters of mercury. And just to show you one last thing, the vapor pressure lowering, delta P, is the P naught of water minus the P of the solution of water. So it's going to be the 31.8 minus the 31.1, sorry, 8. Duh. Okay, I did that right. Okay, 0.8. And that's going to be 1 millimeter of mercury. And I wrote all this out beforehand. I want to just make sure I entered my number wrong because I wrote it down wrong. So 31.8 times 0.9676. Yes, it's 30.8. So I'd written it down wrong. I wanted to make sure I did the math right. And that is the end of this video. We'll do another problem in the next video.